Okay, today we're going to talk about calculus in motion. Now, we already talked about this first lecture. In fact, first lecture, I intended to go through all of the calculus the types of calculus we'd be looking at this school year. And really, I only got through calculus in motion, but you still have that sheet with the different things we'll be covering. And you had the calculus assignment went over last class period, so I've got all that graded and back to you. I'm actually a little proud of that. On Moodle.
Oh, okay.
If you go to the assignment on Moodle, you'll see uploaded the feedback, just like with labs.
Perfect.
And so today we're going to be really going through this again, just giving it a more careful look and looking at some examples that are beyond what we did that first lecture. So first, just reviewing of what calculus is. Right, we use it so much, and I mentioned it that first lecture, but in algebra-based physics, we learned that the average speed or average velocity was the change in position delta x over change in time delta t. And then if you want to find the instantaneous, then you have to decrease your time window over which you're making those measurements to something that's approximately no time. And so you have to take the limit as delta t approaches 0 of delta x over delta t to get the instantaneous speed. In calculus, the symbol d represents that we're taking the limit. Maybe I shouldn't have delta t approaches 0, but it is. The d means the limit over a very, very tiny piece. As I look at this, I'm thinking maybe I didn't actually use proper nomenclature in that middle line. But the d is an infinitesimal amount of change. And so taking this definition, applying it here, the limit as time approaches 0 of delta x over delta t is just dx dt. So when we say the derivative dx dt, it's the same as delta x over delta t, except for in the limit of very small delta t. And so acceleration was defined as a is dv dt. And of course, from the previous slide, v is dx dt. And we started with those in class the first week. Now that we've actually talked about what speed is in class, it's good to come back and just be reminded of that and see, that's where they come from. It's nothing shocking. It's the definition of what speed is. It's the definition of what acceleration is. So jumping right to a practical example. Suppose an object moves in one dimension such that at any given time, its speed is described by this function. How can you find the instantaneous acceleration? So this is a question of how. Not do it, but how.
Acceleration, wouldn't that take an integral because you're finding the area under that curve?
Other way.
It would be derivative?
Derivative, because you're finding the slope. You're finding the rate at which the velocity is changing.
Aren't you finding like that time, like from that time frame?
What you're describing is how you would find the distance traveled.
Right.
The integral of v dt gives you the distance traveled.
Okay.
The derivative, and so how far does it travel in 10 seconds? That's where you do that.
Okay, but acceleration, derivative.
Yeah, so the acceleration is the rate at which velocity is changing, hence the derivative. So let's go ahead and do that. Let's find what the equation for acceleration is. So we've had a lot of practice with these things of late, haven't we?
Simply the derivative, right?
Yep.
Okay.
So what's the derivative of this function? What rule do I have to use? Product rule. And this is very much like what you had in that first assignment, right? So I'm going to have 10 and then derivative of the first times the second plus the first times the derivative of the second.
Can you see the actual problem and then take the derivative?
Yeah, it was right there. That's why I had it started like this so we could see it. It's right there. And so there I've done the derivative. And notice I'm not being nearly as explicit as I was when we first did the derivatives. Just I want to make sure that you could show this is how we do it and not just, hey, I'm able to get an answer. And so notice they all have e to the minus 0.7t, so I'm going to factor that out. So I have 20t minus 7t squared times e to the minus 0.7t. Remember, there's the 10 out front.
Right.
So 10 times 2 is 20.
Right.
And 10 times 0.7.
Gotcha.
So there's my acceleration as a function of time calculation. It was just a derivative. I say just a derivative. To most people, that's hard. To you guys, that's something you've studied up on, so it's background knowledge. So I look at this, and now I want to talk about what it all means. So notice the speed. What's going to happen to the speed over time? Like at time 0, what's the speed going to be?
Make that 0, multiply that with 1, which you just make it 10t.
Well, at time
that would
0,
go away.
it's going to be 0, right?
0.
At time equals 0, your answer, speed is 0. What about at time equals infinity? I have infinity squared
Which is infinity.
times e to the minus infinity, which is
Massive number.
no
Infinity squared is larger than negative infinity.
Isn't something to the negative infinity like
Just a fraction.
infinitely small decimal some point? Like point
Yes, that's right.
So it's basically
It's
0.
basically 1 over infinity, so
Right.
it's 0. So we have an infinity times a 0.
Infinity squared.
Well, yeah, infinity squared.
Yeah.
Infinity squared times 0.
Right.
What did we call that in class 2
Uh,
weeks ago, a week ago?
Indeterminate.
Indeterminate, right? That would be indeterminate. And remember I told you in physics, we often don't use L'Hopital's rule. We just use orders of infinity.
Mhm.
Which one goes to 0 or infinity faster? Okay, so we have infinity squared versus an exponential. Which one grows faster?
the infinity squared.
It's the exponential.
Why?
Because, well, 10 to the infinity is bigger than infinity to the 10th power.
Because you
That's
could
true,
have
yes.
any number, like the n.
Just, you repeat that sentence, you said 10 to the infinity is bigger than 1.
Then infinity to the 10th power. Even though they're both infinite, right? As you're going there, infinity to the 10th power is not increasing as rapidly as 10 to the infinity is increasing.
Could you scroll over and show the derivative again?
Sure.
Just so I make sure I got it right.
So our velocity is going to be 0 at time 0 and 0 at time is infinite. What about in an intermediate time? Let's say time is 1 second. Our velocity in 1 second, whoops, wrong way. At 1 second, it's going to be 10 times e to the minus 0.7. Well, 10 times e to the minus 0.7 is a finite number. You can put it in the calculator and see a number. So the speed is not 0 in between. So we have a function that starts at 0 and ends at 0 and has speed in between. So, go ahead.
Where can I find this?
Physics 252 lectures on OneNote. Are you in OneNote? Okay, so scroll down a bit. Now scroll up. Okay, I didn't know where we were. Scroll up some more. Yes, right. 2 more blocks. Yeah, 2 more blocks. This is a big block.
Yeah, it's huge.
Okay, so we have past the here.
That's what we're doing for. Okay.
That's where all the stuff I do in class would be. Sorry about that, everyone. Okay, so Now that we've established that it's going to be starting at 0 speed, ending at 0 speed at infinite time, and not 0 in between, we have the question, when is the speed the greatest? This is a calculus question at its root. How do you find, using calculus, when this function is at the maximum?
Don't you take the second derivative or something?
Well, first you take the first derivative, and then you check to see if it's maximum or minimum with the second.
Yes.
Okay, so that's how you find both maxima and minima, or putting it together, extrema. So if I want to find when the speed is the greatest, I'm going to have to say dv dt evaluated at t, and I'm just going to put tm for t max equals 0. That's how I determine when I have a maximum or minimum speed. Now, I can look at the equation I already did because I already calculated the derivative, right? I calculated the acceleration. When the acceleration is 0, then you're going to have no change in speed. You're going to be maximum or minimum, or it's possible that it's an inflection point where it goes like that.
Right.
So a graph is always very useful, and I do have a graph on the next slide, but I want to do the math, and then we're going to compare looking at the graph. So I know what this equation is. Or writing it out, as I like to say, in the most provocative form, TA multiplied by 20 minus 7 TA e to the minus 0.7 TA. And actually, I should have used wise color decisions here to make life really simple for you. Okay, so I have 3 terms, so I use 3 different colors for them. Because those terms are multiplied together, if any one of them is 0, then they're at 0. Provided the others aren't at infinity, which we kind of talked about at the infinite time. So what condition would make the first one, the magenta one, be acceleration 0? Okay, that was real easy. Chapman was wise in jumping in on the first one. Okay, then going to the green one. What condition makes the acceleration 0, so it's a minimum or maximum for the green term?
7 times TA is 20.
Okay, when 7 times TA is equal to 20, he said, and I'll write this over here, 20 minus 7 TA equals 0, so 20 equals 7 TA, so divide both sides by 7, and you have when TA is 20 over 7, so I'm just going to put 20 over 7 rather than, something slightly less, slightly less than 3, 2 point something like 86. And the blue one, at what value of TA is the blue term 0?
Can you take the natural log of 0?
No, you cannot.
Then I have
The natural log of 0 is minus infinity. That's why you can't take it.
Right.
It'd be 0.
So that means that TA, since you have a minus sign in the exponent, and I'll put approaching because that's technically what it is. So those are the 3 places where our speed is not going to be changing. Well, we've already identified it's 0 speed at the first one and the third one. Those are clearly not our maximum speed answer. Yeah.
Why would A be 0? Why can't you be
Because if you have TA being 0, if exponent becomes 0, and e raised to 0 would be 1, not 0.
Right.
And we're looking for when our equation.
Are you talking about this one here or this one here?
The bottom.
Yeah, this one here, e to the 0 is 1.
Right.
And so time equals 0, this term gives me 1. And then it gets smaller as time gets larger. So as time approaches infinity, this term is approaching 0.
Okay.
So we had three extrema, but two of them we had already analyzed when I was just asking what's the speed doing. And so the answer has to be just the middle one is the maximum. The other two are the minimum. But then we go to what David said. I said that has to be. How would we verify that? David, you said?
Second derivative.
Second derivative. So if we take the second derivative, that will tell us for sure if it's a maximum or a minimum. So d second v dt squared, or if you prefer, that's dA dt. And so taking the derivative of that, I'm going to have 20, I have to use the product rule again, 20 minus 14t e to the minus 0.7 ta plus 20t minus, that's a minus sign.
Yeah.
Just to look like a plus sign.
7t times 0 times negative 0.7.
Yes, I forgot that. Thank you.
Times e to the negative that.
Whew. Did I really want to do that? No, I didn't want to, but I had to. And so once again, trying to write this in the simplest form, everything has e to the minus 0.7 ta in it. And then I have 20 minus 14 plus, or no, minus 14 again. Minus 14 minus 14, right?
Check. Yeah. So minus 14 minus 14. And then
Plus 4.9 t squared.
Yeah.
So that's my value of the, we actually have a name for this, by the way. It's the jerk. The jerk is the name for the rate of change of acceleration. You're not going to be tested on that.
Oh, good.
I learned that from a student, actually. I was like, I don't know that there's a name for it. He's like, it's the jerk. And I looked it up and he was right.
So should those t's there in the parentheses be ta?
Oh, they should have been t's because I was just taking derivatives.
Okay.
I'm going to apply it at ta to see what's going on at time a. And so if I put in my time ta, if I put in 20 over 7 for ta, all I care about is the sign. The exponential is always positive, so that's positive. And then I have 20 minus 28 times 20 over 7 plus 4.9 times 400 over 49. So 28 divided by 7 is 4. 4 times 2, or 4 times 20, excuse me, is 80. So 20
Minus 80 is negative 60 plus.
minus 80 plus, and of course, 4.9 over 49 is 1/10. 400 divided by 10 is 40.
So it's a positive number. No, it's a negative number.
So that's negative.
So that
So-
means it's a minimum, right?
So we have a negative, and now we have what I was taught long, long ago. Happy face with the pluses, sad face with the minuses. So if that second derivative is positive, then it's a minimum. If the second derivative is negative, it's a maximum. That's what that means.
That's hilarious.
And the reason we can understand simply, if the second derivative is positive, when you move away, it's going to be increasing. The second derivative, when you move away, it's going to be decreasing. Question?
That was mine.
That was right. Okay. So because
Actually,
go ahead.
so our answer of -20, or it's negative value. So it's negative, so it's a minimum.
Right.
But we're looking for the maximum acceleration.
Or no, it's a okay. I have the words maximum and minimum in the wrong spots. If you're at the top, you're at a maximum. I feel like an idiot suddenly. Right. If you're at the top, it's a maximum. If you're at the bottom, that's a minimum.
Right.
I wrote that wrong. I probably said it wrong too. My figure was absolutely correct. My reasoning at the end was correct, but I had the words wrong.
Okay, so if it's positive, it's minimum.
If it's positive, it's minimum because it's going to go up.
Because it's going to go up after that point. Gotcha.
And if it's negative, it's a maximum. I'm so sorry I had those words wrong. I'm so glad you corrected me. Maximum. So this here, a positive times a negative is a negative, hence it was a maximum. Here's a graph. So we have a graph and we see here is the maximum. And the maximum comes down here. And it's somewhat less than 3. Right, because 3 would have been right there. So it matches our 27ths. And we can see that it was at 0 here, and it's asymptotically approaching 0 as time gets large.
No.
Correct. That's what asymptotically means.
Asymptote?
Asymptotically.
Oh, I know what you're talking about. Asymptote.
Never actually heard that word.
When I was in high school, my teacher said asymptote. And so when I got to college and my teacher said asymptote, I was.
It's asymptote.
Yes, it's asymptote, apparently. But my high school teacher is forever my hero, and so. Okay. Now we had when is speed the greatest? When is the acceleration going to be the greatest? How would you find it? We're not going to find it, but how would you find when the acceleration is the greatest? Yeah, we found when speed was the greatest. We did the second derivative to see if it was a maximum or minimum.
Right. But if we're taking the second derivative, isn't that acceleration?
It's right.
Well, we started with velocity, so the first derivative was acceleration. The second derivative was the jerk.
It's right before.
Because we started with velocity, we weren't starting with position. Right, second derivative position would be acceleration. Second derivative
So
velocity.
what does the jerk measure?
That measures how the acceleration is changing. And so if the jerk is 0, actually, that's when you're going to be at maximum or minimum acceleration.
Okay.
And so we actually could come to this calculation of the jerk there and say when that's 0, well, that's 0 both at time equals infinity and at, well, not at time equals 0. Right? We have to take the quadratic and find the roots of that quadratic. And those are what we're going to have. One of them is going to be a maximum acceleration, one's going to be a minimum acceleration. And we're not going to do it. But that's how you would find them.
So basically, we couldn't say exactly when the acceleration is 0. We can only say the acceleration gets close to 0 at 0 and infinity.
No, we would say the acceleration is at a maximum. Now, when the acceleration is 0, we've already determined that. That was when we had maximum speed. To find the maximum acceleration, we have to set the jerk equal to 0 and find the times. And we have infinity. Well, at infinity, this term here is 0 because it's flat. That's not going to be a max or min. And then we use this and use the quadratic to find the two roots. And one's going to be maximum positive acceleration, one's going to be maximum negative acceleration.
Gotcha. And because the graph is all positive, we use the positive answer, right?
Well, because I said what's the maximum acceleration, I said positive is the maximum. The negative is the minimum.
Right.
Okay, so why am I going through this? That's math tools that we need to use from time to time to maximize something or minimize something. In second semester, we'll do a brachistochrome problem where we are calculating the minimum time for light to go from point A to point B. And what that does is show that Fermat's hypothesis was correct, that light takes the path of least time. So we're going to be using that second semester and maybe other times. Now, I have here the integral of the velocity, and that goes to what Oksana talked about initially. Since velocity is dx dt, if I multiply both sides by dt, I have v dt is equal to dx. Integrate both sides, I have x is equal to the integral of v dt. So that's why I have this integral shown. If I want to find the distance that the object has traveled, I need to find the integral.
Ooh, that makes sense, because you have velocity unless you work backwards.
Right. So this equation here, now notice I did not put limits on that. So delta x is equal to that, the integral. And I did the integral, I looked it up, honestly. You know, could I have done this integral? I could have. I would have done integration by parts twice, because you got that t squared. Remember we talked about that. Oksana did our example with it. So I could have done it, but once you know how to do these things, once you've shown that you know how, I'm happy with you not having to do it every time because of time involvement. Believe it or not, when I was in graduate school, I had a professor who thought that you didn't really understand a graph unless you made it by hand. And so my office mate, he had copious amounts of data. He plotted on the computer, but our boss required him to do it by hand. And so he went through the data. He took like 1 out of every 50 data points and plotted it by hand to recreate the graph the computer made, so he could show that he made it by hand. That's just a lot of work for no good reason, except for he was old school, didn't really trust computers. You got to remember, I'm a bit older than you. Easy. So, yeah, that's why I wouldn't require you to do it. I'm on a test, obviously. You'll have some like integral tables as necessary, but I'll expect you to do the kinds of integrals, like polynomial integral, that kind of stuff,
Okay.
without having to have a table.
So you wouldn't, on the test, you'd have something like this on a table?
Yes, I would. Right? Otherwise, I only got 2 hours in this exam, and that integral is going to take me half of it. Yeah. So, going back to when you first learned an integral, how did you calculate an integral when you first learned to do an integral?
How did we calculate? Can you tell again how you calculate what?
In calculus class, going all the way back to when you were in college, which, for David and I is going back a few years. How did your teacher teach you to do an integral?
Rectangles.
You add one to your
Rectangles.
Yeah.
You made rectangles. So you said, okay.
Oh, this.
And you have the left or the right theorem. Do you remember that? You have one option is to make rectangles like this.
Oh.
Yeah, this was a trig thing.
That's using the right rectangles. And then there's the left rectangles. And then there's the intermediate ones, which is what just seems to logically make sense. But since an integral is the function, which the vertical part should be your function, multiplied by whatever small amount is on the horizontal axis, then the area of each one of these little boxes is a height times a little width. And you add them all up and you get the full integral. So the area under this curve is the distance traveled. So if I want to know how far it travels before it starts slowing, okay, that was a perfect line there. Let's just pretend I dropped a vertical line from, the peak. If I want to know how far it travels from time 0 to there, well, one way of doing it is the integral. That's the right way. Another way of doing it is to take my ruler and say, if I go, something like, I'm kind of roughly approximating it, and then make a triangle and a rectangle, and I can calculate the area of the triangle, the area of the rectangle, add them together, and that's the total area under the curve, approximately. Right? I'm trying to balance. And I'm sure my line's a little high. It's not the greatest method if you don't have straight lines to find that area and thus find the integral. So that's the kind of thing that in calculus class we learned to do integrals like that, and we didn't think much of it. We're going to use that over and over this semester. You know why?
Because it's relatively inaccurate.
Relatively accurate, and your comrades without calculus can do that. Right? They can make geometric figures and find the area enclosed by a triangle and rectangle.
Right.
Whereas they can't do the integral. So when we talk about work is integral of force dot dx. And so for us, well, we have a changing force, we can just do an integral. For them, we'll take something like a spring where the force function is kx, and we'll say, okay, we'll plot kx on, straight line. And then if we add up the area under that, hey, look, it's a triangle. And you have 1/2 kx squared is the work. Right? So
it seems like really involved.
It's physics. It's going to be involved. So here's a picture to illustrate. And this is using the left to match them, so you can tell that the integral that they're going to get here from the area of the box, this is going to be too small because they have the systematic error of always being, and it's rising. If it was dropping, it would be too large. Now, my last example, a more practical one. We have a dragster, real numbers. The maximum acceleration for a top fuel dragster is about 5.6 Gs. That's 5.6 times 9.8 meters per second squared. You think about it, you're sitting in your chair and you're being pushed down with 1 G. If you're in that dragster, you're still being pushed down with 1 G, but you're being pushed into the back of the seat as it feels to you, or the seat's being pushed into you as reality is. 5.6 times harder than you're sitting on your seat. That is kind of crushing. So the people driving those top fuel dragsters are withstanding some pretty significant conditions. The speed after 1,000 feet is 330 miles per hour, or 148 meters per second. Yes, Nathan and I took his car up to 135 miles per hour this summer. We were only 200 miles per hour below what a top fuel dragster is doing after 1,000 feet. Only 200 miles. We were close. Well, 195. Actually, I shouldn't. Well, we didn't get a
He drives a Camaro, right?
No, it's a Corvette.
Corvette's good.
By the way, it's a nice car.
Yeah, I love it. He loves it more.
Of course it is.
Yeah. Okay, so we want to try to model the motion of the dragster. And so a first glance says, well, the acceleration is probably at 0 speed, pretty much at its max acceleration. And then as it gets faster, the acceleration is going to drop and drop and drop. And so I suppose that the acceleration was the maximum acceleration times 1 minus the speed over its maximum speed. And as we'll see at the end of today's lecture, turns out that's a really good model. So with this guess at a model, we want to answer a bunch of questions like what's the speed as a function of time, what's the acceleration as a function of time, what's the position as a function of time, how long does it take to cover the 100 or 1,000 feet, and how fast is it traveling when it completes the 1,000 feet. Now, how fast is it traveling when it completes the 1,000 feet in reality?
148%.
Yes. So we know what its actual final speed is. So let's start at the top. What is the speed as a function of time? How do we go from acceleration to speed?
Integral.
Okay, so I start by writing the equation. And you're right. Okay, but so there's the equation, and then I'm just going to substitute. My model says that acceleration is equal to, stay with me now, A0, 1 plus V over V max.
What is V? Is that the initial velocity?
V is the speed at any time.
At any time. Okay.
V max is the maximum speed the dragster can reach.
Right.
Okay, so you said we integrate. What do we need to do before we integrate?
Do we need to plug in what we know? So like we plug in the initial acceleration and the maximum velocity or no?
No, we'll wait till the end because otherwise I'll have to do a lot more writing.
Okay.
And having A0 means something very meaningful. That means 5.6 Gs, right? That means something.
I recall you saying for acceleration, we're taking the derivative.
Well, acceleration is dv dt, but we're looking for v. If we were looking for acceleration, we knew v. That would be absolutely correct.
How are we
Separate
going to
dt to the other side.
Okay, we need to separate the variables. That's what I was looking for. What was your question, David?
How are we going to do? Oh wait.
This is kind of what we did in calculus, the separation of variables.
Okay, never mind. I figured it out.
Remember,
Like,
you were probably in grade school when he did that.
Oh.
I mean, I did take calculus last year, so.
Oh, you did?
Yes.
Huh.
I needed a refresher.
No. Okay. So I need to separate variables. What are my variables? I have to identify the variables before I can separate.
V and T.
V and T. So I divide by everything in the parenthesis that has the V in it. That's the only way to move the V over to the same size dV. Okay. Now I have the left side of the equal sign is only a function of V. The right side of the equal sign, only a function of T. So I can integrate these independently. From V0 equals, hey, it's going to start from rest here, right? So I'm going to put that 0 here. I know there's a little bit of inconsistency in that I'm saying, no, leave the variables in, except when there's zeros because it's going to make less writing.
Yes.
That's the reason I put them in early is because it makes less writing. So it starts from rest. That's why I have V0 is 0 here, whereas what we did the first week of class, I did not put in V0 is 0 because we weren't necessarily starting from rest. T0 is 0 because that's when we started the stopwatch.
So would that be natural log 1 plus p divided by p max?
There's going to be one variation on that, but essentially yes, right? Because I'm going to use a U substitution. Well, because I have 1 plus V over V max, I'm going to say
Let U equal V over V max. Oh.
Here's the thing.
Huh?
I don't know why you.
Derivative of 1 plus v.
I don't know why you don't put values in for the variable.
well, because it's less writing this way.
Right.
And there's also another reason that we'll see at the end of the lecture. There's a second reason that's important.
And to learn, I feel like,
Well, as when we get to the end, you'll see that you can't do it if you put the number in.
Okay.
Yeah.
I understand why V disappeared and y1 disappeared.
Mm-hmm.
Why did Vmax not?
Okay, imagine that we were doing d, we have u, we're taking derivative of u with respect to v.
Yes.
If we're doing it with respect to v, the derivative of 1 with respect to v is 0.
Mm-hmm.
The derivative of v over vmax, vmax is a constant, so I'd have 1 over vmax times derivative of v with respect to v, that would just be 1.
Right.
Well, here we're not doing respect to v, so it remains dv on top instead of dv over dv to make it 1.
Okay, and the only reason is because Vmax is constant.
It's a constant that's multiplied by, yeah. And so with that substitution, I'm going to have the left side becomes integral from u initial is equal to 1 to u final is equal to 1 plus, well, 1 plus v final over v max of du over u. And then we have exactly what Randy said. That's natural log of u. And if I'm going to put my limits in right off the bat, right? We've already gone through the limits and how to evaluate them. If you're not clear on that, you do the upper one minus the lower one. So my result, natural log of u with the upper limit minus natural log of u with the lower limit. But when you subtract natural logs, it's just natural log of the positive one divided by the negative one. So the upper one is the positive one, 1 plus Vf over Vmax divided by 1. I'm not going to put divided, well, I'll put divided by 1 because I gave myself space before I looked at what the lower limit was. So that's the integral of the left-hand side. Except for one thing. One thing because Richard Webb. No, not plus C.
No.
That would be if I didn't have a limit.
Oh, right.
I replaced dv with du, but dv is actually Vmax du. So I need to have times Vmax out here. That's not part of the natural log. That's multiplied by the natural log. So it's Vmax. I wouldn't put it out here except for I didn't have space.
So then doesn't that kind of can't, oh wait, never mind, that one cancel out, never mind.
Actually, I'm going to move that equal sign, put it out front because it just is less ambiguous.
Yes.
Like that. I made that mistake. We all make mistakes. I understand that. You don't lose significant points on the test for a mistake. You might lose 1 point out of 10. But we make them. We understand that. Well, if it's graded on partial credit. If it's one of the ones that's just grade multiple choice, well, yeah. Okay, so that's the left-hand side. What's the right-hand side?
A sub 0 t.
It's a sub 0 t final. So now I'm just going to manipulate this. I'm going to divide everything by Vmax. So I'm going to have natural log of 1 plus V, and I'm going to drop the final, over Vmax equals a sub 0 t final over Vmax. And what am I trying to solve for?
You're trying to solve for, I forget, was it velocity?
For V, yeah. Because you kind of have to know what you're trying to solve for, or things don't work out the best.
Can't we get rid of the absolute value signs because it's
always going to be positive, yes. Yeah.
Right.
In fact, honestly, I think I represent many physicists in saying we're very sloppy with absolute value signs in our natural logs.
Okay.
So the exponential function is the inverse of natural log. And so I'm going to have 1 plus V over Vmax equals e to the a0 t. I said I was going to drop the finals and I didn't there. Over Vmax. So V equals Vmax
Shouldn't the exponent be in the parentheses? Shouldn't the -1 be outside of the parentheses of the exponent?
No, the first thing I have the exponential, and then the first thing I do is I subtract 1.
Okay, I see.
And so I have a -1. I have to put an artificial +1 so it doesn't make non-mathematical sense. So those go away, and I have the e to the stuff -1, and then I multiply across the Vmax.
Gotcha.
So there's the equation for my speed. So at time equals 0, I'm going to have e to the 0 is 1 minus 1 is 0, so it'll be 0 speed. And as time gets large, somehow this doesn't feel right, does it? Because this is not going to asymptote to Vmax, and it should. Right, the speed shouldn't exceed Vmax. I'm guessing see in my answer, well, that's the X answer, not the V answer. Oh, there's a minus sign here. Whew. I was like, I was feeling something was wrong, but I'm like, trust yourself. Don't be a doubter. I should have been better.
Is this lecture recorded too?
Yes. Yeah. So you can go and say, yep, he made that mistake. All right. So now at this point, it becomes, this is a negative exponent here, and there's a minus there.
So it becomes negative Vmax times the e to the negative exponent -1.
So it's going to be like that.
Wow. Oh wait, that's one.
Yeah. A bunch of sign errors, I'm sorry. You can see it all stemmed from writing my starting equation with the wrong sign. And once again, that kind of mistake would only cost you 1 point because it was very beginning and it cascaded through, but it was just one little mistake that is easy to make. Yeah.
Full point.
Oh, okay. So if t equals 0, the initial velocity also still equals 0.
Yeah.
Because that's going to be -1 minus -1.
Yeah, so here's the way it looks in normal form.
Right.
And so if time is 0, it's 1 minus 1 in parentheses.
Right.
If time is infinity, it's 1 in parentheses. Because it's 1 minus e to the infinity, minus infinity, which is 0. Okay, so there we have our speed as a function of time. Now, go ahead.
Like we can do that equation.
Okay, yeah.
What was your question or statement?
No, I was just saying, since I feel like we can do that equation to find out which one.
Yes, that's right. Because I have the next question is, was the acceleration as a function of time? Well, we were given the acceleration, but what was the acceleration as? Our model said the acceleration was a function of what variable?
Gravity.
Not gravity. The model, but the thing up in the right corner. You're looking at the peak acceleration.
Sorry.
The acceleration is a function of
Acceleration.
and speed. The acceleration is a function of speed in the model.
Right.
And now we're saying, oh, what about the acceleration as a function of time then?
Don't you just use the equation that we just
Yep.
calculated and solve for a?
We just solved this, and so we take the derivative of this with respect to time, and we'll get the acceleration as a function of time instead of the acceleration as a function of speed.
Okay, so we just take the
Yeah. Which, because we only have 1 minute left, I'm not going to do it. I'm going to stop doing work and just explain things from here on in because I want to get to the part where you see why I didn't put in Vmax. So how long does it take to cover? How would you find the equation for the time to complete the trip?
You use the position formula where x equals a bunch of things.
Well, no, because that was only true if it was constant acceleration. This is not constant acceleration.
Well, that's right.
So I have to take this velocity equation, let's take the red one because that's written out nicely, and I have to say v is dx dt and integrate. And so here I've done the work. There's the equation for x as a function of time. The problem is You can't solve this equation for time. It's what we call a transcendental equation. You can't analytically solve it. You can still solve it, but not analytically. That is, you're not going to put it, something in your calculator and get numbers. But what you can do is you can graph it. So I've arranged it so this here is the left side. This here is the right side. And then using the values for A0 and the final speed that it has when it finishes the race, I made a graph. And the place where those lines cross, right here, and then I just zoomed in, that's going to be the time when the race is done. And so using that, I get 4.183 seconds, which is too long. It was 3.7 seconds, I told you. And I get the speed at the end of the race is 116.7 meters per second, which is wrong because I told you it's 148 meters per second. So right now it looks like my model is horrible, right? But how can we improve it? There's one simple change I can make to improve it. One thing that's definitely wrong. Well, I did put in the values. I put in my Vmax was 148 meters per second and my A0 was 55 meters per second squared. I put those in to get those values. But one of those is really the wrong number and you know it's wrong. Which one's wrong?
Well, you have second squared versus second.
No. Wouldn't it be the maximum speed?
The maximum speed is definitely wrong. What I put in for maximum speed was the speed it has at the end of the race. Not its maximum speed. If it kept going for another 1,000 feet, it'd be going faster. So I actually used a fit. And if I put the maximum speed as 304 meters per second, then I plot the graphs again. I get the time. And it comes out to be 3.701 seconds is the time it takes. That's only off by 1/1000th of a second. And the ultimate speed is 148.3 meters per second, only off by 0.3 meters per second. The model is actually pretty good with an ultimate speed of 304 meters per second possible for this thing. And so that's a reason why I keep the variable in there, because I didn't really know what Vmax was. And in the end, I fit to Vmax to find what the maximum speed was. If I had put in a number 148 for it early on, I would have been forever solved. All right, have a great hour and a half until I see you next. Remember to do your reading quiz before lab.